Picture this. You've got a perfectly humming corporate data center, right? Everything is totally fine. Then a well-meaning engineer decides to plug in just one extra backup cable between two switches, just to be safe. But they forget one absolutely crucial safeguard. Within seconds, the entire network just flatlines, literally grinds to a complete halt. No emails, no databases, just silence. So how on earth does one single cable cause $1 million company to totally collapse? Well, welcome to the high-stakes world of network architecture. What you just saw in that nightmare scenario is called a broadcast storm. It's basically the silent killer of networks. Think of your network like a city's road system. When you plug in that redundant cable without thinking, you've accidentally built a massive roundabout with 0 exits. A simple broadcast frame comes in, goes out the backup link, loops right back, and then multiplies. And it just keeps going. These frames loop indefinitely, completely clogging the links and totally overwhelming the switch's MAC tables until the whole system just crashes under its own weight.
Now, if you've got your Network Plus basics down, you are in the perfect place today. Welcome to this explainer. Today, we're going to step into the shoes of a senior network architect. We'll explore exactly how we survive these kinds of catastrophic failures using some pretty brilliant automated protocols, and even better, how we transform that raw, dangerous redundancy into pure, high-speed performance.
Okay, let's take a quick look at our project blueprint for the day. First up, the broadcast storm. 2, RSTP, the intelligent traffic cop. 3, the redundancy bottleneck. 4, EtherChannel, the superhighway. 5, configuring the highway. And finally, number 6, the architect's real-world advice. All right, moving into part 1, the broadcast storm. Redundancy without intelligence. Let's see why this raw redundancy is actually a recipe for disaster. So in the real-world job market, your boss is going to demand network redundancy. For sure. If a switch dies or someone accidentally cuts a cable, the business absolutely has to keep running. But here's the catch. Redundant physical links naturally create loops. Without a protocol to manage them, Ethernet frames will literally just loop around the network forever. What we really need is a clever way to keep those physical backup cables plugged in, but logically turn them off until the exact moment we actually need them. And that brings us to part 2, RSTP, the intelligent traffic cop, preventing the storm. We need someone out there directing traffic. Enter Rapid Spanning Tree Protocol, or RSTP. You can think of RSTP as a really smart traffic cop stationed right at that endless roundabout we talked about. What this protocol does is map out the entire network and then deliberately puts up a barricade, what we call a discarding state, on very specific ports. The physical cable is totally still there, plugged in, but user traffic is blocked. Boom, the loop is broken. Now, what's really interesting here is the evolution. The older version, the original spanning tree protocol, took about 50 seconds to react to a broken link. Why? Because it had to wait through these incredibly long listening and learning phases. In a modern corporate enterprise, 50 seconds of downtime is an absolute eternity. You'd have people screaming. But RSTP? It bypasses those old timers entirely. It reacts in mere seconds, rapidly shifting from that discarding state straight into a forwarding state to keep the business online. It's a total game changer. So how does it pull this off so fast? Well, by cleverly labeling the roads. Our traffic cop assigns specific roles. The root port is your absolute best path to the center of the network. But the true hero here is the alternate port. This is your instant backup road. Since RSTP already knows this alternate path exists, if that main link fails, the traffic cop instantly yanks the barricade off the alternate port, completely skipping those old, slow listening states. Let's slide into part 3, the redundancy bottleneck, wasted potential. Because, as it turns out, our brilliant traffic cop just created a wildly frustrating new problem for us. Imagine your company is paying for 4 high-speed 1 gigabit per second cables between 2 massive data center switches. Naturally, you want 4 gigabits of speed, right? But remember, RSTP sees redundant links as highly dangerous loops. So what does it do? It leaves one single link open and completely barricades the other 3. You're literally paying for 4 gigabits, but you're only getting 1 gigabit of usable bandwidth. The rest is just sitting there doing absolutely nothing. Which takes us right into part 4. EtherChannel, the superhighway, unleashing bandwidth. Let's see how we build our way out of this bottleneck and trick our traffic cop into letting us use all those roads at the very same time. Just look at these dense bundles of cables connecting these switches. In a real data center, you'll see massive chunks of these everywhere. We definitely don't want to leave all that expensive equipment just sitting, blocked, and idle. To fix this, we use a really cool technology called EtherChannel. What EtherChannel does is it takes multiple parallel physical links and conceptually wraps them together into one single giant logical link called a port channel. And here's the magic. Because RSTP now looks at this and sees just one massive road instead of 4 separate dangerous ones, it doesn't block them. We finally get our multi-lane superhighway fully utilizing all the bandwidth the company actually paid for. On to part 5, configuring the highway. Command line implementation. Because as a network admin, you gotta know how to actually build this thing at the command line. We don't just blindly plug cables in and hope for the best. We actually use dynamic negotiation protocols to make sure the links are healthy before the switch bundles them up. You basically have 2 choices here. LACP is your open industry standard. If you want the switch to actively start forming the channel, you literally use the keyword active. On the other hand, if you're using Cisco's proprietary protocol, PAgP, you use the keyword desirable. The key takeaway? One side must actively initiate the conversation, or your highway just won't form. So the crucial point to remember here is that EtherChannel is incredibly strict, almost paranoid. Every single physical port you're trying to bundle must have the exact same configuration. I'm talking the same speed, same duplex, same VLANs, the whole shebang. If you try to bundle a 1 gigabit port with a 100 megabit port, the switch will straight up reject it and throw your ports into an error-disabled state. And honestly, in the real world, you want this strictness. It protects you from accidentally building a chaotic, mismatched highway. Okay, so once the highway is up and running, how do the cars actually drive on it? Well, the switch uses something called load distribution. It's important to know it doesn't just chop your data frames into tiny pieces and scatter them. Instead, it carefully examines the MAC or IP addresses of your data, runs a quick mathematical algorithm, and then pins that specific flow of traffic to one dedicated physical lane. This is super vital because it makes sure your data arrives in the exact right order, which keeps your end user applications perfectly happy and stable. Finally, part 6, the architect's real-world advice, building for the future. Let's take a step back and look at what this all means for you and your career. And this brilliantly illustrates the exact difference between just knowing the basics and actually thinking like a senior architect. Look, anyone can plug in a backup cable and just let RSTP block it. But a truly great engineer optimizes their environment. By layering EtherChannel underneath RSTP, you instantly survive those catastrophic failures while simultaneously maximizing every single dollar your company spent on infrastructure. It's a win-win. So you now have the skills to build a robust, loop-free, insanely fast Layer 2 network. But in a modern enterprise, you know traffic needs to move between different departments across totally different subnets. So here's a thought to chew on for your CCNA journey. Now that your Layer 2 superhighway is paved and ready to go, how exactly are you going to use routing to direct traffic across multiple VLANs? Keep that question in the back of your mind as you continue your studies. Thanks so much for joining me on this explainer, and I'll see you on the next one.